Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our lesson on minimum and maximum values, right? So last time we did an example, which was here, and we were able to identify the critical points. Wait, so here's a question. We were asked to find the local minimum and maximum, as well as the saddle points of this quadratic surface equation. And we took partial derivatives, right? And then we equated them to 0, and then we were able to find our x as well as corresponding y values, and we were able to identify the critical points. And then we used the second derivative test. So we took second derivatives, right? We used the formula, we plugged it in, and then we plugged in each critical point, and from there we were able to determine whether it's a saddle point, a local minimum, or a local maximum. So let's actually do some exercises related to that, just to get a feel for how it exactly works, right? Also because I'm trying to do my homework. Okay, so yeah, so some exercises. We'll do some exercises related to that for now. Um, okay, where are you? Okay. Uh-huh. Cool, cool, cool. Okay, and we're here. Oh, for number 2, yeah, we're gonna start at number 2. Don't worry. We're being asked to find the local maximum as well as the local minimum, right, of our particular, and saddle points, right? So my goal actually in this course is to try to identify the pattern, keep repeating it until we get it, right? Because that's academic math for you, of this particular function, right? That's the idea. We can use a calculator or a computer to graph the function with a domain and viewpoint that reveals all the important aspects of the function. We're not gonna waste our time doing that for now, but you guys can do it. I did it in the previous video just to show that it works. Okay, we have 4 minus x to the 4th plus 2x minus y squared, right? 2x squared. So that's our function. So first we take partial derivatives. More specifically, we try to find our critical points, because these points will help us identify if it's a saddle point, a local minimum, or local maximum. So we take its derivative. We get 0 minus 4x cubed plus 4x minus 0. And so here we have minus 4x cubed plus 4x, right? And then my f sub y is, well, we treat these as constants. Here we have, we treat everything as constants. Right, so here we have negative 2y. And then from there, we can now find, or we plug them in to 0. We equate them to 0, right? Because we want to find critical points of x and critical points of y. So here we just divide that by 4. So we can factor out that 4, right? And so we actually just get x cubed minus x. Here we got y equals 0. here we get, I believe I could equate these two. Or better yet, I could factor it out. There we go. And then from here, well, we see that x is 0. Here we see that x squared minus 1 is 0. And let's continue. So the issue, okay, this works. There, plus minus square root of 1. So we have 1 and negative 1, right? So here we actually have 3 values of x. But we only have 1 for y, right? And then from there, well, we have critical points. So our critical points, I was able to find it in this previous one. Yeah, I took their derivatives. Oh, and then I plugged them in here. So that's how I was able to get them. But here I have no choice. I can't really plug it in anywhere. Yeah, I can't really do that. So I have like a couple of x and a couple of y values. No, I only have one y value. Yeah. Do we have critical points? Not sure, if I'm gonna be honest here. We have y equals 0, but we have a couple of x values, right? Let me just double check and see if I'm doing it right. Yeah, I feel like it might not exist, and I'm just wasting my time. So we're gonna double check just to be super, super sure. Okay. Oh, my bad. I forgot to. Let me see. Yeah, x fourth to x squared. Okay, so we did get the partial derivatives correct, right? I set them both to 0, and I get, okay, so I get the, oh, so they are critical points. Okay. So if I'm shown with a case like this, I'm gonna say we have 0, 0, right? We have 1, 0, and we also have negative 1, 0, right? So those are our 3 critical points. And then from there, we use the second derivative test, right? Where we basically get our derivative, we multiply its xx and yy, we subtract that to their xy squared, right? Because that was the formula. I'm just writing it in a short way. Oh, there. Okay, so let me get their second derivatives, right? And then once I get their second derivatives, what do I do now? Oh, now I plug it in. Okay, so once I get their second derivatives, I basically plug it in. So f xx. So I look at my sub x and derive it again. So I have negative 12 x squared for this one, that first term. And then my second term, I have plus 4. And so that means my f sub x, just look at my critical points, right? So actually, let's do that later. Let me do that later. All right, let me do f sub y first. So here, if we look at my y value, Well, I take this derivative, I just get negative 2. So this should be negative 2. And lastly, if I take my xy, I can look at my y, take the derivative in terms of x. So I just get 0, right? So here I get 0. Let me just double check. Here I take the derivative of y, oh, I just get 0. So Clairaut's theorem tells us I could do it either way. And they both achieve the same result, which is 0. And so from there, I just plug it in. So my f sub x at my critical point 0, 0. Well, this is just 4. My f sub x at my, or my f sub y, rather, at this critical point is negative 2, right? And then my f sub xy is always 0. Okay, so actually I don't need to, I can completely ignore my f sub y's and then my f sub xy. I just need this, right? So let me go ahead and plug in. So here at 0, 0, well, this is just f sub x, and I plug in my x here, which is 0. So I get 4 times negative 2 minus 0. So this is negative 8, which is less than 0. And if it's less than 0, it's a saddle point, right? So this is a saddle point, 0, 0, right? There we go. Now I look at my other critical value, 1, 0. If it's 1, 0, here I get negative 12 plus 4, right? This just gives me negative 8, right? Let me just see if I got that. See, that's what calculus students are for. Oh, look at that, another saddle point. So these two are saddle points. What else? My negative 1. Well, here, oh, my bad. My bad, my bad. This is not a saddle point. It's this. So that's, let me plug in the 1. I get minus 8 times negative 2. So I get 16, which is greater than 0. And then I check if my f sub x is less than or greater than 0. Here I see that my f sub x at that point is actually less than 0, right? Because I get negative 8 less than 0. And so if it's less than, but it's greater than here, what was it? So my second derivative is great. So the formula tells me I get something greater, but my f sub x tells me I get something less. If I get something less, I have a local maximum, right? That's what I have. Okay, let me actually just do this. This is greater than 0. I don't care about what the number is. I just need to know if it's less than or equal to 0. Less than or greater than 0, right? So this is a saddle point. This one is a local max, right? This point. And here, what do I get? Here I get, this is negative, no, negative 1. I actually get the same thing. I got negative 8 times negative 2, so I get 16. This is actually greater And then here, it's kind of the same thing. So this is less. And so this is also a local max, right? And so those are my answers, right? Okay, let me just double check, see if I got. Yeah, so my local maximum values are at 1, 0, and negative 1, 0 in terms of x and y coordinates. And my saddle point is the 0, 0, right? Let me just plug it in, see what happens. So my saddle point is 0, 0. Oh, I enter it as a comma separated list. So my local minimum is nothing, so that's D and E, does not exist. My local maximums are 2 points, so I have 1, 0, as well as negative 1, 0. And if I submit, see what happens. Check, check, check. Oh, what was this? Remove the grouping symbols around multiple terms in your list. What does that mean? Comma separator. Grouping symbols. Huh? Uh, I got it right. Else me. What issue is this now? For my local max. Okay, it's correct. However, I have to remove the grouping symbols. What is my homework doing? Formatting issue. Yes, it's a formatting issue. Oh, flatten the list. Local maximum. What is this? Grouping symbols around multiple terms of your list. Local max, local max. Wait a minute. I think I know the issue, kind of. Or find the points where the function has the. No, it says values. Yeah, they're asking for the z values. Okay, my bad, my bad. Yeah, so if this makes sense. What's really happening here, once I get that local max, so I got like 2 here, I basically want to plug it in. So get max values. So in other words, get the z value, right? So I basically just want to plug it in my original function as well as my other one. So what's this gonna be? If this is 1, 1, 0, all right. Yeah, 1 and 0, I get 4 minus 1 plus 2. That's 4 minus 1, 3 plus 2, that's 5. So here I get 5, right? And then when it's negative 1, I put negative here. Well, I'm still gonna get negative 1 to the fourth. That's negative 1 times negative 1. That's positive 1 times negative 1. That's negative 1 times positive times negative 1. That's positive 1. So I still get 4 minus 1. This was plus 2. So it's still 5 again. So I get like 5 for both. Now what's the... I got like 2 5s. So I think my answer should both be a 5, right? Okay, let me comma separated lists. Should be 5. Let me see if that makes sense. I have 5 for both. Should just be a 5. Okay, got it. Nice. Yeah, I was looking for the output. Anyway, okay. Number 3. I'm gonna attack this homework a bit differently than I used to. So here again, we're being asked to find the local min and max. But here we're focusing on the... Oh, should have just... What am I doing? Here. There we go. I'm gonna make this number 3. I'm gonna attack the other one later. My function here is f of x, comma y. This is equal to 2x cubed minus 6x plus 6xy squared. Right? So what's the first thing I have to do? I have to find critical points. That's always what we've been doing. And so I take its f sub x. So this is 6x squared minus 6. Then this is 6y squared, right? My f sub y is, no, these are 0. This is, I leave my 6x be, but then I multiply 2, so this becomes 12x. And this is y, right? And then from there, let me continue. So what are my critical points here? I basically equate them all to 0, right? Notice here, I can divide the 12. I get this instead. These are 2. Okay. Y is basically 1 over, I don't know. Either one of them is 0. So these are critical values that we found, right? These two. What else can we find? Here, I guess I can make this like this. Oh, look at that. I get a unit circle. What else can I say about it? I guess all of the points here within x and y. So what would that be? My x could be a 0, my y could be a 1, or vice versa. When I say my x is 0, how do you even solve this? What the... Well, I guess I just isolate one of them. Let me just do that. So here I get like y squared equals, oh, but then I don't think it works that way. You get like a unit circle here. I get that for my y. Now the positive case, here I just pick basically. If my x is 0, then my y is 1. If my y is 0, then my x is 1. So these are two other points. I have no idea what else I could choose. I got 3 though, and I think that should be fine. I don't know, unless I mess something up. If I mess something up, then I don't think so though. It's one of these things. Okay, let me just double check. Apparently I get a unit circle. Oh, so I plug in x equals 0 to the first one. And then I get some other point. So here, if I plug in my x is 0, then my y is, well, y is either plus minus 1. And similarly, if I plug in my y is 0, well, then my x is plus minus 1 as well, right? Huh. Okay, so the difference here when we approach this problem, because here in the previous one, we get y, we get x, and then that's it. Here, there's an x and a y, so it's a system of equations, right? So we solve x and y. Here we get x is 0 and y is 0. And then we plug that into the other one. And then here we get this part. And so our critical points in this case are these. You can either have 1, 0, negative 1, 0, 0, 1, 0, negative 1, right? Those are our 4 points. And then from there, let's use the second derivative test. So the second derivative test, let me just turn on my light because it's getting dark. So my second derivative test tells me I get fxx. So here this is, okay, 12x, right? Because I'm treating x as a variable. Nothing, nothing. Okay, so it's 12x, right? My f, y. So here I look at my y, and oh, I get 12x. Look at that. My fxx is equal to my fyy. Now if I look at my fxy, I look at my y here, I do it in terms of x, well, I get 12y, right? So here I get 12y. And then from there, well, now I compute each of these, or now I use that derivative thingy. So actually, let me just plug it in. So here I get fxx, fyy. Actually, I should have just computed all of them in terms of the critical points, right? So in this case, I can do it for all. So let's say for 1, 0, what is this, 12? For 1, 0 of my YY, also 12. Or no, anything with FXX and FYY should just be the same, right? This is equal to this. This is just 12, right? My FXY, however, is 12 times 0, which is 0, right? And so if I use my formula here, well, I get FXX, so 12 times 12. Let me just do it for all. So I multiply these two minus this squared. So here I get 12 times 12, 144 minus 0. So I get 144, which is greater than 0. And since my f xx at that point, let me just do this. I don't need this. This is greater than 0. This is greater than 0. If they're both greater than, it's a local min, right? So this is a local minimum at 1, 0. Now, if I look at my negative 1, 0, let me plug it in. Actually, negative 1, 0. Okay, a lot of computation here. Well, quite computation. We get negative 12, right? And then my f xy is again 0. So if I do my second derivative test, well, this is greater than 0, right? Because negative 12 times negative 12 is, again, 144 minus 0, so that's greater than 0. But then my f sub x is actually less. And so that means this is a local max at this particular point in my quadric surface. Then lastly, we check. We have like a couple more actually. So here I do, I think this was 0, 1, right? Well, this is also equal to my fyy. Here I both get a 0, right? Now here comes the interesting part. What if actually we'll see if we get there. 0, 1. 0 times 0, that's 0. Minus, this is minus xy, so 12 times 1, 12. I square that, so 144. I get 0 minus 144, so I actually get a negative value here. So if it's less, then this is a saddle point. Right? At 0, 1. And then lastly, oh yeah, my fxy is negative 12, right? Because if I plug in, or no, not negative 12, 12. Then I do the same thing. My fxx at 0, negative 1 is the same as my fyy. Here I still get 0, right? And then my f xy is -12. But then I square it. So it doesn't matter. I still square it, I get the same thing. So this -1 is also a saddle point. Right? See if we got those values correctly. So at 0, 0, 1 is a saddle point. 0, -1 is a saddle point. 1, 0 is a local minimum. -1, 0 is a local maximum. And then we evaluate these things. So let me just do, let me make it more general. Evaluate min slash max values. So let me just quickly do that. Here again, I evaluate min slash max values. So my, okay, let me do, wait, my saddle points, I don't need to actually. I have 2 here, 0, 1, and because these are points, right? 0, 1. Then I enter them as a comma separated value or comma separated lists, right? So 0, 1 and 0, -1. Then my local maximum values. So local min at 1, 0. So I just do my function at 1, 0. This will give me my local minimum. So that would be 1, 1, 0. Boom. This is 2 minus 6, -4. Right? Done. And then my f of, so this is my max value this time. -1, comma 0. So here I just change these to a -1. Oh, so this becomes -2. But this becomes +6. So now I get 4. So indeed, I'm right. This is a maximum value. We can literally see it. This is positive, this is negative. So there's a clear idea there. In my z-axis, this one's bigger, this one's smaller. Right? So if I look at my max, it's a 4. My min is -4. Right? Okay. Cool. Let me see if we got that. Nice, got it. Okay. And we'll continue for about a couple more. We'll do 3 more stuff. Now we'll just, I'm not gonna cut the video anymore. We'll just continue and see what happens. So let me again do this for like 3 more stuff. So it's just getting used to this idea of, again, well, getting used to the problem, right? That's what we want to do. So again, we're being asked to find the local max and the local minimum, as well as the saddle points. So let me quickly do that. Here's our function. Okay, this I'm gonna try to do it a bit quicker. Kind of like a test. So first things first, we find their critical points. How would I do that? I get their f sub x. So here I treat y as a constant, y 64. I put my 64 out. 1 over x, was that? If I take the derivative of 1 over x, this is the same as me saying give me the derivative of x to the negative 1. So I do negative x minus 2. So I have negative 1 over x squared, right? And so I have, if I multiply, I have minus 64 x squared. And then that's just 0, 64 over y, done, right? Now I do f sub y. So here, I treat my y as a variable, x as a constant. So this is x. This one's 0 plus, or no. Now I have minus 64y squared. So this is just reversed. And then from there, I put 0, right? Here I put 0 as well. I guess I do get something here. I can see, what can I see? I can see a parabola. I can see that. So here, let me translate it. I get 64 x squared is equal to y. Then maybe, how do I connect these two? Oh, so now I have a system actually. I have a system here. Here I do the same thing. 64 y squared equals x. And then from there, it's my decision on which one I want to plug in. So I guess I'm just going to plug in this x to here, because why not? Or this y to here. So I'm going to say 64, my y, which is this, square that, that's equal to x. Now I solve for x here. Then I plug in my x here, find y. So I got 64. This is, I believe, 64 squared. What is that? That's 409 divided by x to the fourth. I can then kind of put this up-ish, right? So I'm going to say this is equal to 64x to the fourth over 4096. And then I can do this. I can make this 164. So I'm left with x. What else can I do? Oh, I basically now have x to the fourth divided by x is 64. And then I get x to the third is equal to 64. Then I get, what is that? So that's 64 to the power of 1 over 3. Oh, look at that, x is 4. Done. Right, so I've solved for x. I plug it here. Now this is 4. That's 4 times 4, 16. 64 divided by 16 is 4. So y is, funny enough, also a 4. Yeah. And then from there, now I have my critical point. So I only have 1, which is 4, 4. Right? Based on this x, I got a corresponding y value. Let me just see if I actually got that. Yeah, so here I'm trying to check everything I'm getting just to be more efficient. Let me see. This function is not defined. Oh, wait. Or did I didn't mess up, no? I don't think I did. Okay. I hope I didn't mess up. So system, x is 4, y is 4. Okay, got it. I was about to panic. And then again, we use the second derivative test. right? So I just plot these critical points. So I have f of x is equal to what? Based off of here, y is 0. Yeah, I got that. This is negative 64 over this. How do I find the derivative of this? So the derivative of this is, well, negative 2. I like doing this. I don't want to do quotient rule. I get negative 2x. Negative 2 minus 1, negative 3. And so I get negative 2, 1 over x third. And so if I multiply 64 to 2, well, now I get 128. So here I get 128 over x cubed, right? Done. Now, let me do my f sub y, fyy, x is 0. Oh, I get the same thing. I just switch it up with a y, right? Simple as that. And then from there, let me get my fxy. So here, let's say I look at my y. Now I take the derivative with respect to x. Well, I have 1, right? Because if I treat this is 0, this is 1. So I actually just have 1. Let me just check just to be sure. Now if I go here, I take the derivative in terms of y, this is 0, this is 1. Also same thing. Yeah, and then from there, I just plug in everything. So let me see. So this one, I'm going to get in terms of my critical point, right? So I get 128 over 4 cubed. 4 cubed is 64. 128 divided by 64. So this is 2. Now if I do my f sub y, funny enough, this is also 2. F xy is 1. Yeah. And so I'm just going to do my second derivative test where I multiply these two. I get 4 minus 1. And that's 3, so that's greater than 0. My f sub x is greater than 0. And so, if they're both greater, I'm pretty sure I get a local max. Or no, local min. My bad. Yeah, if they're both greater, I get a local min. And this is specifically at that point. And there we have it. No saddle points, none of that. Okay, and then now I evaluate. So here I am evaluate anything. So my min or max values. My saddle points, I don't in this case. Right? So my minimum, well, I have none. So I do f of 4, 4. Let me see. Oh, so now this is some interesting functions. I got 4 times 4. I add that to my 64 over 4. Then I think I subtract, right? No, I add again. Plus 64 over 4. Oh, look at that. I got 16 plus, what's 64 divided by 4? 16 times 2, that's 32. I get 48 as a local min, right? My local minimum is 48. My local maximum does not exist. And my saddle points also don't exist, right? And there we have it. Okay, let me submit, see what happens. And still loading. Got it. more. Okay, so find local min and local max. What number was this? Number 5. So again, same idea. So find, oh my bad. I totally forgot about the function. So we have f of xy is equal to x cubed plus y cubed minus 3x squared minus what? 9y squared minus 9x, right? Then from there, I find the critical points. So what are these? Well, I take their partials. So here I get 3x squared minus 6x minus 9, right? Yeah, otherwise I just take it out. Minus 9x, that's minus 9. 3x squared, that's minus 6x. X cubed is 3x squared. Okay. And then, my f sub y. So my f sub y is 3y squared minus 18y. That's it. Okay, now I make them equal to 0. And so here, I actually don't need to do any systems, right? I just need to solve for x, solve for y, that's it. What can we see here? We can actually simplify. This becomes x squared minus 2x minus 3. You can also do the same here. Y squared minus 6y, right? Then from here, now this one's quadratic formula, maybe? Or something to factor. Here, I'm just going to factor. X plus minus. Oh no, this plus 3, no, minus 3 plus 1. Because if I add negative 3 plus 1, negative 2, if I multiply. Okay, cool. Here, I could factor out my y. Here I get y is 0, y is 6. Here I get x is 3, x is negative 1. Now, the interesting thing is, which one do I pair it with? Do I pair negative 1 and 6? Or do I pair 3 and 6? Or is it just all of these combinations, right? Could be any of them. Now that's another thing I have to look at. Because previously, if there's only one of the variables, I could pair them with all of them, right? I could just do that. But here, in this case, I have to think carefully how to do this. Yeah, so for my x, we have 3, negative 1. Oh, shoot, it's all of them. So it's all of the combinations of these things, right? All combinations. So I'm going to say my critical points are actually a couple of them. So we have 3, 0, 3, 6, negative 1, 0, negative 1, 6. Great. Then from there, I use my second derivative test. So I get the second derivative. So this is going to be f sub x sub x. I look at my f sub x. Here I get 6x minus 6. Then f sub y. I look at my y here. Here. I was looking at the wrong thing. 6y minus 18. Right? If I'm not totally mistaken. Yeah. And then my f sub xy. So maybe I can take a look at my y. Oh, 0. Right? So I just have to multiply these two stuff, and then I get my d. Right? Okay, so let me start with the first value. 3, 3, 0. Let me just do that. So when I plug in the 3 here, I get 18, if I'm not mistaken. Minus 6, so that's 12. Here, if I plug in my y, for that same value, well, I get negative 18. Oh. So in this case, I get a negative value, right? This times this is negative. I don't need to worry about, yeah, so this is immediately a saddle point. That's a saddle point. Okay, let's test out my 3, 6. So this one is, if I plug in my 3, I still get 12, right? If I plug in my y, I get something different. Here I get 6 times 6, that's 36 minus 18. Well, now I got a positive value actually. So I get 18 here. And so from there, my d of this is greater than 0. But here my f(x)(x) is also, at that point, is also greater than 0. And so this is actually just a local min at that point, right? What else can we say? So another critical point. Negative 1 and 0. Well, here, if I plug negative 1 in my thing here, I get negative 6 minus 6, so I get negative 12. Now, if I plug in my y value, here I just get negative 18 again. And look at that. My d at that point is positive, but my f sub x at that point is negative. So I get a local max. So it does take long to do these types of stuff. Then lastly, I get negative 1 and 6. So, oh, I just realized there's a pattern I could do here. Once I know some of them, I could just, well, assuming that it's separated, right? That's the assumption. But anyway, I'm trying to think of shortcuts while doing this. So here, this is negative 1 and 6. I already did 1 and 0. And 6. So here, this is negative 12, because I know. Then my f sub y, this is negative 1, negative, or 6, my bad. 6, I know this is 18, because I already saw it here. And so this is negative. So this is immediately a saddle point at that point. Okay, we were able to get 2 saddle points. Okay, negative 1, 6 is a saddle point. 3, 0 is a saddle point. 3, 0 is a saddle point. 3, 6 is a local minimum. And negative 1, what's this? Local minimum. Oh, didn't show the, oh, negative 1, 0 is a local maximum. Okay, now we evaluate all of the min and max values, right? So what is this? If we evaluate all of them, we get to see that for my local max, so my F is actually just negative 135. My saddle points, I don't need to. My minimum, however, oh no, my bad. My local max is 5. And then my local min, 3, 6. Let me see. I get, okay, negative 135. And then my saddle points are just there. Okay. Okay. So my local maximum is 5. My local minimum is negative 135. One thing we haven't tried doing yet is finding. Anyway, saddle points are 3, 0 and negative 1, 6. So 3, 0, negative 1, 6. Submit, see what happens. Done. Okay. There's this last item. I'm just gonna. It was like a cosine function. That was interesting. Yeah, I might want to just skip that part because at least we got the idea, right? Just trying to be fast here. Um, and we also are given an interval. So that one's also interesting to look at, kind of. Oh, that one's interesting. So everything's DNA for that problem. I'm gonna skip that part. Oh, I got one wrong. Okay. Um. hmm. Okay, I might as well do it because I got something wrong here. Anyway, just do it. I thought I could get away with it, but I guess not. Anyway, okay. So here we're being asked to find. I just memorize the steps and we should be good. So we have this. Uh, number 6. And my function here, it's actually a function of two variables again. We have f of xy. Here we have 4y cosine of x, right? And this is 0 less than or equal to x, less than or equal to 2 pi. And actually, yeah, so that's an interval, right? So here we find our, again, find our critical points, right? So get their partials. F sub x is, well, we leave 4y as is, because that's a number. My cosine, however, I have to, that's a negative. It's actually negative 4y sine of x, right? Let me just see if we got that part at least. Okay, we got that part. And then for my f sub y, here in this case, I leave this b. Then my y is 1. So that's a number. Then I equate them to 0. Oh, now here's a tricky part. When are they 0? Right? So here I could actually say, oh, look at that. I have a function of y and x here. Here I only have a function of x. So I'm going to use the x I get here, plug it in here to get the y value. That's one thing I could do. So here my cosine is actually just, my x could be a 0. That's one. Somewhere in between, so if I do a unit circle, actually no, my x is not 0. I don't think my x is 0. Because cosine 0 is 1. Yeah, my bad. My x is pi halves, I think. Yeah, that's one of them. Pretty sure that was one of them. And then my other one was when it's 3 pi. 3 pi. Yeah, another one that's 3 pi half. And then 2 pi is just 1. So that should be the full rotation. Yeah, those are my x values. So I plug those in here. And I basically just get 0 for all. No, actually, when I do sine pi half here, I get 1. So my y is 0. When I do sine 3 pi half, I should also get 1. Or I think it was -1, if I'm not mistaken. Oops. 3 pi third is 0? Crazy. Yeah, so this is -1, so y is just 0, pretty much. I don't see any more or any other values that would work. Uh, these two conditions, f of x. Oh, okay. So I actually get pi half comma 0, as well as 3 pi half comma 0. So I actually get those two, right? Uh, yeah, okay. Yeah, he messed up there. GPT messed up. Anyway, so those are the critical points, right? You want to kind of think of it like a system. So my critical points are the following. So pi half, as well as 3 pi half, right? And then from there, I use my second derivative test. Wait, did GPT get it? If they got it, then I should be good. Both are saddle points. Where are the saddle points? Oh, I get those two are saddle points. Okay. Let me just see. Actually, no, I'm not confident. Let me just go for it and do it. Okay. Let me see. Ah, fine. I'm gonna try. I have like a couple of tries. But those are both saddle points. That's one. Another one is 3 pi over 2 comma 0. Those two are saddle points. Um, yeah, those two should be saddle points. Okay, got it. Nice. Um, critical point, minimum, maximum of f. Okay, we have an absolute max and min, absolute max and min, absolute max and min. Find shortest distance d. I'm trying to gauge like which one looks points closest, dimensions. Okay, so you have to do those. Okay, I'm gonna try doing, should I do the first one? Like a contour map. Uh, Using the level of curves. Actually, let me try this part. I think this one is just, yeah, because these are Z values. I'm gonna show my screen. Here we're being asked to find we're being given a contour diagram. We're given this function, right? So it's a quadric surface. We have Z values here because it's a contour map. These are level curves when Z is equal to something. So when Z is 3.2, we just, in 3.2 here, we got something there. So using the level curves, use the level curves to predict the location of the critical points of F. So what are the critical points of F? How do we determine whether F has a saddle point? Does F have a saddle point? A local max, local min. Use second derivatives to test your predictions. If an answer does not exist, enter DNA. That one's actually tricky. Yeah, I'll admit that one's tricky. Um, Let me see. I'm trying to skip through. Oh, there we go. We have something here. Let me actually just go through this part, maybe. Find and classify the critical points. Okay, let me do this one first. Yeah, so that we can find that other one. Using a graphing calculator, computer, solve this equation numerically. We could do that. What? Find shortest distance. So that's another thing we have to look at. Rectangular box, absolute max and min. We're going to go through that as well. Absolute max and min. Proof. I'm not going to go through that. Okay, let's actually go through this example. So see here how like I'm just trying to play around with the things here. Okay, I'm going to go back. So I'm just referring to the textbook in this case. Usually the textbook gives me so much info. Right. So example 4. Am I sharing the right thing? Okay, just making sure. Because I did mess up at one point. So here we're going to find and classify critical points. Classify meaning, is it a local minimum? Is it a local maximum? Or is it a saddle point? So here we want to find and classify these critical points of a certain function. We're going to copy and paste this graph here. Okay, let me copy and paste. Cool. Okay, let me go here. Oh, went over. I'll go there. Okay, so that we can get that example 1 out of the way. Mainly just for this. Okay, so given this contour plot, how in the world can we tell, right? No. Okay, this is the function. So the function is 2 variables, 10x squared, y minus 5x squared, minus 4y squared, minus x to the 4th, minus 2y to the 4th, right? So that's the function. Oh, also find the highest point on the graph of f. So we're actually looking for an absolute max here. Okay. So again, actually there's a trick here. We want to do the same thing. I just realized. So again, we want to find the critical points. You want to use the second derivative test on those critical points. And then, yeah. Oh, but there's an issue. Because in my problem, oh no, but my function's given. Predict location of the, oh, so once I get that z value, how do I predict? Ah, at what z value is it? Hmm. Okay, let's see. We have a similar problem though. So I guess the first thing we want to do, well, based on the task book, is to find critical points, right? Uh, so again, we do an f sub x here. This is 20x, 20xy minus 10x, 0, 0, minus 4x cubed. Okay, then my f sub y is, so this is 10x squared minus 0 minus 8y, 0 minus 8y cubed, right? And then now we plug them in, make them 0. So here I can isolate a 2x. This becomes 10y minus 5 minus 2x squared. This is equal to 0. The another one was this one. So this is 5x squared minus 4y minus 4y cubed is equal to 0. So actually, once we get this, we're gonna have to do our best to not eliminate any of the values here. Okay. Um, so here we can see that this x is 0, but we're also seeing that this is equal to 0. And so to solve for that, when x is 0, we just, well, equation 5. So the other one, y is 0. So that's another thing. So what happened was, if I make x 0, I plug it into the other side, I get this thing, y is 0, right? And then, so that's a critical point, right? Second case is when this is equal to 0. And so I get that, actually get an interesting curve here. Uh, oh, uh, okay. If y, so it's an approximation. Goodness me, it's an approximation. That's interesting. Okay. How in the world do I go about that? Yeah, because I get an approximation. Let me just screenshot the rest of these values. Or actually, yeah, let me just screenshot all of it. And these are approximates, right? They're rounded to 2 decimal places. Uh, wait, how do I, there. Okay, that's interesting. So how do I do that previous one then? Right? What? Predict the location. Oh no, but here I just have to find the points. So actually, there's a cheat here. I don't need to use the contour map for number one. I just need to find their local max, min, and saddle block. That's it. Never mind. So I just wasted a bit of time there. I didn't need to find exactly that. right? So here I'm just going to say saddle point. Okay. For my number, yeah, I mean, yeah, let me just do it. So for number one, basically I'm doing the same thing, right? I'm doing the same thing. I just have a different function. So let me just go ahead and attack the problem like this. I didn't need to use the contour map. I could, uh, but I don't need to. I just need to find at what point is the local max and min. So it's actually this is a pretty easier problem. So here I have because I have a function. That's why. If I'm only given a level curve, I don't know. So this is 4 plus x cubed plus y cubed. And I think the other one was, oh, this is minus 3xy, right? I erased the whole thing. Minus 3xy. Okay. Uh, so I attack the problem like so. I find critical points, right? So I get their f sub x and f sub y. 0, 3x squared, 0, 0, oh, no, not 0. Negative 3y. F sub y, 0, 0, 3y squared minus 3x. So here, see how it's just kind of reversed. And then when I get my critical points, I set them to 0. Here I actually get x squared minus y. Here I set this to 0, I get y squared minus x. Right, so those are just two things you can notice. And then from there, I'm just making this a bit quicker, x squared, y equals x squared. Oops. X equals y squared, right? Now I plug in. So my y is x squared. I do x equals x squared squared, x to the fourth. I divide both by x, I get 1. I get x cubed. And so my x is 1 over, or 1 cubed root 3, I get 1, right? My y, I get 1. So my critical point, I only have one critical point here. And that's 1, 1. And then from there, I use the second derivative test. So it's the same process, right? Same process. So fxx, so I look at my f sub x, I get 6x minus 6x, that's it. Fyy, I look at this, I get 6y. Simple, right? And then I look at my critical point. Now, what is this? This is d of 1, 1. Oh, my bad. I look at fxy. Almost forgot that. I look at my y. I derive it in terms of x. So this is 0. This is negative 3. Right? And then, well, now I plug in what I know. So fxx of my critical point, which was 1, 1. This is 6. Fyy is also 6. Now I get this. So my d of 1, 1 is just my 6 times 6 minus negative 3 squared. I get 36 minus 9. I get a positive number. So I get something positive here. My f sub x at that critical point is also positive. And so I get a local min at this point. And now I can plug in to see where exactly is that local min, what's the value. But that's really all I need, right? So this is one. And then does not exist for the others. My local minimum. I don't even have a saddle plot. I don't have anything pretty much. That's all I have. I'm gonna bet this works. That was the cheat there. Okay, got it. Oh, I messed up one part. Saddle point. You do not have the correct number of terms in your comma separated list. Comma separated list. Why is that? Huh. Okay. So I have a saddle point, but I don't see it. uh, okay. Let me double check. Local maximum, minimum, and saddle points. I take their derivatives. Okay. X is equal to 1, y is equal to... Oh, I have 0, 0. Where in the world did I see that? I didn't see 0, 0. I mean, if you look at it, I kind of do have it. Yeah, because I immediately thought of y equals x squared, x equals y squared. And then from there, I could have plugged in this. X equals x to the fourth. Uh, it's not obvious, I would say. Right? Like it's like from here, I mean, yeah, yeah. If like we see there's a 0, I guess we just have to put it in. If we see that it satisfies the equation in some way, then we just have to plug it in. Let me see what this is actually. This is 0. And so that's also equal to my fyy. And so my d in this case is, oh, and d is a negative. Yeah, because that's 0 minus 9. So it's negative actually. So there's my saddle point at 0, 0, the origin. I didn't know that. Yeah, I was just too careless, I guess. This one's 0, 0. And done, right? Attack the problem, then need the contour plot. But I could check though. I could check what it is. But not now. Okay, let me just continue following function on set D. Okay, here I have to find the absolute maximum and minimum. So I might just go directly to do that. Maybe. Find the shortest distance. Oh, let's do one problem like that. Or can I do one problem on that? Because these are mostly absolute max and min. Okay, let me do one problem on short distance and then immediately implement it. Points on the cone, points on the surface. That was another one. Dimensions of a box. These are all watch it. So I might just... Okay. Let me do a short distance problem. Yeah. Okay, let me do one of those. Okay. I'm gonna... Okay, where's my short distance problem here? That's the unfortunate order of things. Let's do an example 5. So here we're being asked to find the shortest distance from a particular point to a plane. Oh, from point. Is this the same problem as the Homer? Oh, it is. I think it might be the same problem. Oh, no, it's not. My bad. This is 1, 0, -2, all the way to some plane with this equation, right? X plus 2y plus z equals 4. Okay, so the shortest distance from any point xyz to this point 1, 0, -2 is just the distance formula, right? But however, if xyz lies on that particular plane, well, that's another issue. Oh, if xyz lies on that plane, then we make z in terms of x and y because we want it to be in the actual plane itself, right? So we have to minimize that. Oh, what? That's interesting. And then from there, we square it. Okay. And then we get their partial. Huh. That's interesting. So here, we assume it lies on the plane, right? I think that's what it wants us to do. Or something else completely. Where's my z? Oh no, we just assume it lies on the plane, right? So here's the steps. So find the distance from x, y, z to 1, 0, -2. That's the first step. So d, distance formula, x minus 1 squared, y minus 0 squared. I'll just put the whole thing. I'm not gonna leave any assumptions here. And then z plus 2, right? And then we're gonna say, if it lies on that plane, then we simplify z. So here we replace z in terms of x and y, right? So here we had x plus 2y plus z equals 4. That's where we got that information from. Now we turn it into z is equal to 4 minus 2y minus x. And I think it's in that, oh no, my bad. It's not in that order, but you get the idea. Now z is in terms of x and y. And then now we replace that in our distance formula. So x minus y, x minus 1 squared, y minus 0 squared. And then here I have my z. So this is 4 minus x minus 2y plus 2. So it's 6 minus x minus 2y squared. Right? And then what's next after this? Now we want to minimize d. So we want to minimize that distance by minimizing the simpler expression, right? And so basically here we square it. That's it. We square it. Then we copy. And then from there, okay, I see we can solve these equations, right? Now we can actually treat this as f of x comma y, right? We want to make it as simple as possible. We square that thing. And then we solve for it, right? So here, again, we find critical points. We use the second derivative test, right? So let's go ahead and do that. So let's go ahead and take f sub x. So here, this will give me, I treat this as a variable. I get 2 times x minus 1 times 1. What else? This is 0. This is plus 2 of this thing. Whatever's inside. And then I do a chain rule, so I get -1. So I get that minus here. Right. And then from there, well, I got 2x minus 2 minus 12 minus, or plus 2x plus 4y. Right? Cancel, cancel. Here I get 4y minus 14. Right? Oh, this was a plus. My bad. 4x plus 4y. Oops. Minus 14. And then from there, okay, I'm also going to do my f sub y. And so that's going to be 0 y squared, that's 2y. 6 minus x. So again, we take that derivative plus 2 of whatever's inside. Do a chain rule. This is 0, 0, minus 2. And so we get minus 4 here. Right? And then from there, let me go ahead and try this. 24 plus 4x minus, no, plus 8y. So here I actually just get 4x plus 10y minus 24. Right? And I'm going to set them all equal to 0. And then from there, we solve systems of equations. Critical point is actually just 11 over 6, comma 5 third, right? And so from there, well, I now use my second derivative test, right? And so here they kind of did it for us already. So I'm just going to let them do it for us here. So here I get my f sub x at that point is 4, which funny enough is actually equal to my f sub y, which is also 4. And then my f, oh, wait a minute. My bad, my bad. This is my xy. And then my fyy is 10. And so here I already see, okay, my second derivative test is positive. Oh shoot, wait, is it positive? Oh, it is, yeah. Because 40 minus 16 is 24. Yeah, so my d at this point is positive, as well as my f sub x at that point is also positive. And so I get a local min at that point, right? I get a local min. Uh, there's an intuition that this is an absolute minimum. Because there must be a point on the given plane closest to this. Okay. If x is this and y is this. Okay, so after we get that critical point, we plug it in, right? And then after we plug it in, then that should be it. So the idea is to get the critical point, plug it back in to the distance formula, and then we'll see it from there. Local. I'm still trying to like wrap it around my head. How can we be so sure? The distance from any point, so any point to 1, 0, -2, and it lies on a particular plane. I'm trying to wrap my head around it. If, let's say, that point lies on that plane, it's a if it's a plane that it doesn't have. I just realized if it's a oh, so we can use local minimum and local maximum in planes as well to find its shortest distance to the point. So it doesn't have to be, oh, okay, let me, huh, well, that's interesting. So you can use the idea of local min and local min uh, to find the shortest distance from a point to a plane. And I'm going to assume this is not, yeah, this point is definitely not on the plane. Because if I plug in 1, 0, -2 to the plane equation, it's not there. So obviously it's not there. Uh, yeah, so that's interesting. Because if it was there, then the shortest distance would have been 0. Because it's literally not there. There's no distance. Yeah. Okay, let me go ahead and do that, right? So now we have that local min. Well, now we can just plug in distance formula, right? I don't even think I needed to do this second derivative test. I just needed to do this. Okay, so let me say when my x value is this and my y value is this, then my distance formula would be x minus 1 squared plus y. So basically, I just plug everything in. So I have 1 over 6 minus 1 squared plus 5 over 6 squared plus. Then I have this 6 minus x plus 2y squared. And then that should be, I think that's right, right? Yeah. Then if I plug everything, oh, I did 11 over x, 11 over 6. And this should give me 5 square root of 6 over 6. And so the shortest distance from there to that, from that particular point to this plane is that one. So we find the local minimum of a plane, which does sound weird, right? Because a plane looks like this. But apparently there's a math thing. There's something mathematical about it that using that particular concept, we're able to find the shortest distance from a plane to a point. Honestly, I would just think of like getting a normal vector, right? What if we do that actually? You get the normal vector. This is n equals 1, 2, 1, right? But then the problem is, how can you really tell if you're going to get close to that point, right? So yeah, that's another thing. How can we find points there? Right? Like I'm thinking about it. I don't think it's gonna work, right? Anyway, okay, before I run out of time here. Uh let me do this here. So again, we're gonna find the shortest distance. So directly to number 10. So find shortest distance D from this point. That's 3, 0, -2, all the way to this plane. X plus Y plus Z equals 2, right? Cool. Okay, so I do a distance formula first, right? That was my first step. So find distance from, let's say, X, Y, Z, all the way to this point. And the moment if it reaches 0, then I guess... Okay, if I plug it in, this is 3, 0 minus 2. That's not equal. So that's not on the plane, right? So this is x minus 3 squared, y squared, z minus, or z plus 2 squared, right? Then from there, now I want to find or replace, right? So here I want to replace z in terms of x and y. So here I have x plus y plus z is equal to 2. I want to replace that with z being equal to 2 minus x minus y. So from there, let me just do a distance formula. This is x minus 3 squared, y squared, 2 minus x minus y, so 4 minus x minus y. I added a 2 here, right? Then from there, okay, I do a d squared, which is equal to my function, right? So this gives me this as my function. And then from there, I find critical point or points. And then I plug in. All right, I don't even need to take the second derivative. Don't see the reason why. Okay, so I find f sub x. So here I treat this 2x minus 3 chain rule times 1. Y squared, nothing. This is again 2 times whatever's inside. I do a chain rule, I get -1. So this is -2. Then if I simplify, this is 2x minus 6 minus 8 plus 2x plus 2y. So I get 4x plus 2y. Minus 6 minus 8, 14. Right? And then from there, this is equal to 0. And I do my f sub y this time. So 0 to y plus 2 times 4 minus x minus y. I do a chain rule, I get -2 of that. And then from there I get, so this is 2y minus 8 plus 2x plus 2y. So here I get 4y plus 2x minus 8, which is also equal to 0. Then from there I solve these linear equations, right? let me see. I guess I can divide them by 2. So if we just say these are equal to 0, I could say they're just equal to each other, right? Like I could do that. Wait, I'm not gonna try to do that. I'm just gonna go with the safe substitution. So here I get x. Kidding. I got 2x. It's not erasing. Okay. Here I got 2x plus y minus 7. Here I get 2y plus x minus 4. Yeah. And then from there, I just keep on going in my system. So here I get y is 7 minus 2x. And so I just plug that in here. So it's 2, 7 minus 2x plus x minus 4 equals 0. And then from there, well, I just continue my system. So y is 7 minus 2x. This is 14 minus 4x plus x minus 4. So minus 3x in this case. Well, that 14 minus 4, that's 10. So I get 10 minus 3x, which is equal to 0. Oh, and then look at that. I get 3x is equal to 10. So here I get x is 10 thirds. Then here I get y is equal to 7 minus 2, 10 thirds, 20 thirds, 3, 21, 1/3, right? So those are my two values, right? I hope I didn't mess it up. Yeah, this is 14 minus 3x minus 4, 10x. No, not 10x. What am I saying? Minus 3x equals 0. Yeah, I did get it. Yeah. Okay, I'm not gonna doubt myself. I'll doubt myself when I get it wrong. So those are my two values, right? And then I plug it in. Plug in to distance formula. So apparently there's that concept in math where you can do this. I'm just surprised that it works. So d is this thing. My x is 10 thirds. I subtracted to 3, right? Plus y squared, so 1/3 squared. Then 4 minus x. So 4 minus x minus y squared, right? Then, okay, let me do this myself. So I should get, this is minus 9, 1/3 squared, right? This is 1/9 plus 1/9 is 2/9. This is plus, and then this one is 4 minus 11 third, 3, 12, 1/3 squared, so plus 1/9, 3/9. I actually just get 3/9. I can simplify, so I get 1/3, right? And then I think I just get 1 over square root 3 here. Then if I rationalize, I get square root 3/3. I get this. And then that's it. That's the shortest distance, right? I hope I got it. Hopefully. not, I have 5 tries, so no worries. Nice. Okay. Now we do absolutes. Let's go for it. Okay. Okay, I'm like, okay, maybe let's do the rectangular box first, because we also have to do that. Oh God, why do I have these first? Dimensions of box. Is it this one? Find maximum volume. So not dimensions. Cardboard without a lid. Because I have watched it there, so find volume of the largest rectangular box. Trying to see which one's the best to do here. It's okay. You know what? I'm not even gonna go through this. I'll skip ahead and go to absolute max and min. Okay, let's go ahead and do absolute max and min. Because I have more problems there to go through, right? Let's see. Okay, so just as for single variable functions, the absolute max and min values of function f of two variables are the largest and smallest values that f achieves, right? So here we have a definition. And so the idea being, well, we let AB be a point in the domain D. So we're saying that AB is on domain D of function f of two variables, of f of two variables, right? So we're saying it's in the domain. Uh, then we're saying that f of AB is either one of the things. So it's either absolute max. How do we define it? Of f on D if it's the greatest value, right? So we're saying it's greater or equal to my function for all xy in the domain, right? And that's the absolute min if it's the the smallest one for all. So yeah, these are just some basic definitions, indeed, right? And from there, we talk about this idea of extreme value theorem, where if f is continuous on a closed interval ab, so this is for a function of one variable, then f has an absolute minimum and a maximum value. So if we go to a recap, extreme value theorem tells us that, let me just do this. What does extreme value theorem tell us? They tell us that if f is continuous, if f is continuous, oh my goodness, continuous, can't spell, on, let's say, closed interval. So there's some interval notation, a to b. Well then, f has an absolute minimum value and an absolute max value, right? So f has, so it has both actually, min and max, right? And according to that closed interval method, we found these by evaluating f not only at critical numbers, but also at endpoints. And this is similar for functions of two variables. So just as a closed interval contains its endpoints, a closed set in R squared is one that contains all its boundary points, right? So a boundary point of D is a point AB, such that every disk with center AB contains points in D and also points not in D, right? So a closed interval also has endpoints, and it contains boundary points. Okay. So every disk with center AB contains points in D, and also points not in D. So that's interesting. Okay. Let me go ahead and just quickly read this, and then I'll just give the definition. So if we have, for instance, the disk D is a set, the rule is x squared plus y squared is less than or equal to 1. It consists of all points on or inside circle x squared plus y squared equals 1 is a closed set, which, because it contains all of its boundary points, which are the points of the circle. But even one point on the boundary curve were omitted, the set will not be closed. So a bounded set in R squared is one that is contained with some disk. In other words, is finite in extent. And in terms of closed and bounded sets, we can say the following counterpart. So here's the counterpart, right? So we're saying if we apply it in two variables, a function of two variables, we're saying that the extreme value theorem this tells us that specifically for functions of two variables. So this tells us that if f is continuous, so there's an update, kind of. And we're saying it's continuous on a closed interval, or not necessarily closed interval, closed bounded set. We're going to call it D in R squared. So in a plane, then f has an absolute max and min. Then f has absolute max and min in D, right? That's all we need. That's all we need to know. Okay. And so to find the extreme values guaranteed by this theorem, well, we know that by theorem 2, if f has an extreme value at x1, y1, then x1, y1 is either a critical point of f or a boundary point of D. Then we have the following extension of the closed interval method. So there's an extension of this. Okay, so here are the steps to finding this absolute min and max, right? So I'll just bluntly state it. So to find absolute min and max, here are the things that we need to follow. So step 1, we have to find values of f at critical points in D. So once we find our critical points, we immediately want to find those values. From there, we want to find extreme values of f on boundary of D. And then from there, the largest of the values from steps 1 and 2 is the absolute max, and the smallest is the absolute min. That's it. So largest is absolute max. So the largest of these values is absolute max, and smallest is absolute min. That's it. Right? That's the idea we want to follow. Okay, so let's do a little or a brief example, right? I'm curious because I have like 1 hour left for this. How many more items do we need? 1, 2, 3, 4, 5, 6, 7, 8. We have like 8 more. 5, 6. Okay, I'm gonna do some of them. Okay. Uh, okay. These ones I might have to. Anyway, okay, let's just go for it. We'll see. We'll see what happens. Example 7. So here we're tasked to find the absolute max and min. So find absolute max and min of this function, right? So here's a two-variable function, x squared minus 2xy plus 2y. And the bounded set is a rectangle. So that's the 2D, that's the boundary. Rectangle D, and this D, okay, let me do it here, because it's a bit long, is a set where given these 2 points, we have conditions, right? So x is in between 0 and 3 inclusive, y is in between 0 and 2. Since f is a polynomial, it is continuous on the closed bounded rectangle. So theorem 8 tells us, so we know f is a polynomial, so it's continuous. Polynomial functions are continuous. When we bound it with this triangle, and by theorem 8, we know there's an absolute max and min. And so first we find critical points. That's the first thing. So here we can notice there is some pattern that we can actually track, right? So f sub x, so we just do it, 2x minus 2y, done, right? We set this to 0. And then we say f sub y, this is 2x minus 2x plus 2, right? Then here we also set this to 0. We can solve for x here, then plug it in here, right? So here we have divided -2, so we get x minus 1 equals 0. We could even do negative x plus 1, but here x is just 1. That's one of the values. And then we plug 1 here, so we can simplify this actually. X minus y is 0. We plug in 1, y is 1. So our critical point is 1, 1, right? That's the first step. Now what's next? In step 2, we have to find the extreme values. Easy. No, I'm kidding. Let me see what step 2 has to say. In step 2, we look at the values of f on the boundary of D, which consists of the 4 line segments, L1, L2, L3, L4. Yeah, because there are 4 lines. On L1, we have y equals 0. This is an increasing function of x. So its minimum value is f of 0, 0 equals 0, and its maximum value is f of 3, 0 equals 9. Okay, we have x equals 3. This is a decreasing function. By methods of chapter 4, or simply observing, we see that the minimum value of this function, it's really just an analysis. Yeah, so here are the extreme values. That's not fun. How do I find these extreme values? If we look at the rectangle, ah, hmm. If my y is 0, we look at the values of f on boundary D. So it's actually making me look at this thing. So to find the extreme values, I want to look at this thing. Okay, cool. So it has 4 line segments, L1, L2, L3, L4. L1, we have y equals 0, right? So f of x 0 is x squared, right? Because if we plug it in here, so f of x 0 is x squared. And we're saying that it's bounded 0 to 3, right? We did mention it here. It was a given. There's an increasing function of x. It is. So its minimum value is f of 0, 0. And its maximum value is the 9, right? So here we basically just see it, right? So minimum or min value is f of 0, 0, which is just 0, right? Maximum value is when my x is 3. Now it's 9, right? And then from there, on L2, we have x equals 3. So we actually look at each of these lines, right? And then, yeah, so here we have when x is 3, we have this, which is now equal to 9 minus 4y. And the condition was that my y should be in between 0 to 2. So I'm looking at L2 here. And then this is a decreasing function of y, right? So maximum value is at 3, 0. So max value is, again, 3, 0, which is 9. Or no, I think it deferred here. Oh, no, it didn't. My bad, my bad. There's a decreasing function of y. Yeah, maximum value is f of 3, 0, which is y. And its minimum is f of 3, 2. And this is 1, right? And then on L3, now we have, on my line 3 here, now we have my y is 2, right? So here I have x comma 2 is x minus 2 squared. And here we see the minimum is at f22, which is just 0, right? F22 this is the minimum. And then my maximum is f of 0, 2, right? Which is not 0, 4. And we can also see it kind of, right? Okay. So here we're just looking at extreme values, basically. And so, yeah, in step 3, we compare these values, critical points. We compare these with, or actually, no, we do L4 lastly when x is 0. So here we have 0y. This is 2y. So here we say, okay. Oh, wait, I forgot to put the intervals. I just realized I forgot to put the intervals. So, okay. So just to remember the conditions here, right? So maximum value is at f, in this case, f of 0, 2, right? And then f of 0, 0 is the min. This is 4. So we really just check all of the combinations here. That's why that's what makes it tedious, right? The minimum in this case is f of 0, 0, which is equal to f of 2, 2, right? F of 2, 2 is also 0. Okay. And so from there, well, which one is the biggest one? The 9, right? The smallest one is 0. So we say this is the absolute min, and this, yeah, one of these, absolute max. Okay, for now here, I'm gonna stop the video. Yeah, because I think we pretty much covered everything we need to cover. And yeah, I'll see you guys all in the next one.